Good morning, good afternoon, good evening. It's your boy Mr. Malaji and I'm back with another video and I'm excited in this video because I'll be going through all the proofs of the theorems that you need for Euclidean geometry. So all of them, all four of them, are going to be covered in this video. So let's have a look at the first one. The first one says that a line drawn parallel to one side, so they're referring to this DE line, parallel to one side of a triangle divides the other two sides proportionally. So what we're required to prove is to prove that this distance there divided by this distance there will be the same as this distance there divided by that distance there. So how do we go about proving that? Let's make some constructions first. So remember, constructions are very important and you have to state your constructions. So my constructions in this case is going to be this line here, of which I'm going to call H1. And that line is perpendicular to AE. So I'm going to construct line H1 from D that is perpendicular to AE. And furthermore, I'm going to construct another line going this way, and that line will also be perpendicular to the AD, and I'm going to call that line H2. So I'm going to draw line H2 from E that is perpendicular to AD. So now that I have those lines, there are two more lines that I still need to draw. There's this line here going from B to E, so line BE, and there's one more line, which is this line going from D till C. And with those constructions, we should start seeing something there. So what I'm going to do is I'm going to realize that the triangle that is at the top, this triangle that I'm going to highlight in orange, I need the area of that triangle. But I'm going to divide the area of that triangle with this particular triangle, which is this triangle there at the bottom. So again, which triangles am I referring to? I'm referring to triangle, or rather, let me state it. I want the area of triangle ADE, and I divide that area with the area of triangle DEB. And us having learnt about areas of these particular ones, we would see that we apply just easily the area formula that we know, which is half base times height. So in this first triangle that I see there at the top, I want to highlight it for you. And that triangle there that I see there, if I'm talking about the area of that guy, then it's just half of the base, and the base of that guy is AD. I'm looking at it in this perspective. The base of that guy is AD, and is being multiplied by the height, which is H2. I hope you're seeing that, guys. And the area of this guy, sorry, let me highlight him. The area of this triangle here, he's going to be half, but the base of that guy is DB, and he also has the perpendicular height, which is H2. That's how you'd calculate the area of that triangle. So now what we notice is that these halves are cancelling, these H2s are cancelling, and so we have AD that is divided by DB. All right, so that we just need a reason for that guy, and so the reason is going to say we have a common corner, which is the E, the common vertex, which is E, and we have a common height, which is H2. So that's the reason for that guy. Then we're going to make another statement, but now we're going to look on the other triangle or from the other perspective. And we're still calculating the area of triangle ADE, the top triangle. But now we're going to divide it with the area of this triangle here. I'm going to try highlighting it, which is going this way. And that triangle is area of triangle DEC. So now let's look at it in another perspective. So I'm saying I'm calculating the area of the top triangle, but this time I'm looking at this as my base. So it's a half, the base being AE in this case, the height being H1, right? And then the triangle at the bottom will also have half. The base of that triangle is EC. And you're still dividing, or you're still multiplying with the height of H1. Then when you cancel these and you cancel the H1, you should see that AE divided by EC is what you get. Same reason. Common vertex. Our common vertex this time is the D. They all meet at the D, and they also have a common height of H1. So we've made those two statements. But how do we consolidate that? How do we make these equal to each other? So what I'm noticing is that these triangles at the bottom, those triangles have the same height. If I put a dotted line there, they have the same height, whatever that height is, and they are between parallel lines, right? So their base is the same and their height is the same. So it should be very easy to calculate the area of those guys. Actually, it should be very easy to see that the areas of those two triangles that are at the bottom is actually the same. So that's my next statement. I'm going to say that area of triangle DEB is actually equal to the area of triangle DEC. And what is my reason there? The reason is that they have a common base, right, and the same height. Now with that being said, then this tells me that these areas here at the bottom are in fact the same to each other. So I can make these equations equal to each other because the top is already the same. We clearly can see that those top guys are the same, and so the bottom guys are also going to be the same. Well, I've just proven that they're the same. So I can make this final statement here that says the area of triangle ADE divided by the area of triangle DEB is actually equal to the area of triangle ADE divided by the area of triangle DEC. So now that I've equated those guys, I've made them equal to each other, then this then follows that the ratios are also going to be equal to each other. So AD with the DB is equal to AE with the EC. And remember the reason for this theorem, you could use proportionality, but I prefer this one here that says line parallel to side of triangle. And there we go. So this is the proof of the first theorem. I hope it makes sense, and I hope you can follow all of this. But basically what we just did is to calculate the areas of each of them, divide them, see that the bases are actually dividing each other, the bases are actually dividing each other, and so we just made this final conclusion here, which says those two triangles at the bottom are in fact equal to each other in terms of their areas. And why? Because they have this common base, which is this DE, if you want to look at it from that perspective, and they have a common height, the same height. And so their areas are going to be the same. I hope this is landing. Let's go on to theorem number 2. Alright, so theorem number 2 then says, if two triangles are equiangular, so if the angles are equal to each other, then their corresponding sides are in proportion, and hence the triangles are similar. So that's what this theorem is saying, and what we are required to prove is this statement here that says the ratios of the sides are in proportion. So how do we go about doing that? The first construction that we're going to make is we're going to construct a line on this bigger triangle. And the line that we're going to construct there, let's call it the PQ line. And why are we constructing that line? So construct line PQ, so much that AP is therefore equal to DE. So what am I saying? I want to draw a point here so much so that this distance here is the same as that distance there. And I want to draw another point here called Q, so much so that DAQ is equal to DF. So I want these sides to also be equal to each other. So I'm basically drawing the smaller triangle inside of the bigger triangle. And then I start with the proof. The first statement I'm going to prove is that these two triangles are in fact congruent to each other. And to prove that they're in fact the same triangles, I need to prove congruency. So the first statement is I'm going to say angle A is the same as angle D. It's given in the picture, right? It came with the question, so that's the reason given. The second thing I'm going to state is that AP is equal to DE. And where do I get this? It's from my construction. So I'm going to put construction as my reason. Then I'm also going to statement number 3 that says AQ is equal to DF. Again, this comes from my construction. And if you remember all your criteria of proving congruency, this is enough to prove congruency. And so we can conclude and say, therefore, triangle APQ is in fact congruent, remember congruent goes like that, to triangle DEF. And my reason for saying congruent is a side, angle, side criteria. So now that I've proven that these two triangles are congruent, it therefore follows that angle P, this angle right there, is in fact the same as angle E from the picture. Because I mean, if they're the exact same triangle, the angles should be the same. And so if I can put a cross there, that means those angles are the same. Then I also notice that angle P is also equal to angle B. Do you see that from just the picture? So if those angles are in fact equal to each other, it therefore tells me that PQ is actually parallel with BC. So it tells me that this line is in fact parallel with that line. And for this, I will put that corresponding angles are equal. Right? Cool. So now that I've proven that those sides are in fact corresponding, or rather parallel to each other because of the angles being corresponding, therefore this tells me that the sides are going to be proportional. So I can state that AP divided by AB, or maybe even the other way around, sorry, the bigger one, AB divided by AP is the same as the other side, the AC divided by the AQ. And where am I getting this? This is the previous theorem that I just proved, right? So I'm going to write that as my reason. This is line parallel to side of triangle. This is from my previous theorem, theorem number 1. Remember, if that line is parallel, it means the sides are proportional. And already, that's what I'm stating right there. But I see that this is not exactly as what I have up there. This one is saying the sides from the two different triangles are the ones that are proportional, not the sides on the same triangle. Ooh, but then, from my construction, I did say that AP is in fact the same as DE. Let's just go back up. Yes, it's exactly that. From my construction, I did say that AP is in fact equal to DE, and I also did say that AQ is in fact equal to DF. That's how I constructed these lines. So I'm going to first state those guys. AD is equal to AP equals to DE, and that AQ is equal to what's the other guy? DF. And for this is constructions, the reason. It's from the constructions I just made. And so if those guys are in fact equal to each other, I can substitute them in there. So therefore, my AB divided by my DE is equal to my AC divided by my DF. All I'm doing is just replacing the AQ that I see there with what it's equal to, which is DF, and I'm replacing the AP that I see there under the denominator with what it's equal to, and that's equal to DE. And on this note, I'm done. I've already proven that those sides are in fact proportional to each other, and my reason will just be. Alrighty, so theorem number 3 says, well, it's this long thing, but what it's basically saying is that if you take a 90-degree angle triangle and you draw a dotted line from that 90 degrees that is going to be perpendicular with the hypotenuse, then what that line does, that AP line, it divides this triangle into two triangles, this one on the left and this one on the right. And what we will find just now with this proof is that these two triangles, these two smaller triangles, are in fact similar to the bigger triangle. And since they're similar to the bigger triangle, since they're both similar to the bigger triangle, they're in fact both similar to each other. So all these three triangles, the bigger one, the one on the left, and the one on the right, are in fact all similar. That's what this required to prove is asking us there. Alright, so how do we go about doing that? First thing is I'm just going to look at this triangle that is this side, and I'm going to compare it with the bigger triangle. Alright, so in triangle ABP and the bigger triangle, which is ABC. What am I noticing that is the same there? First of all, angle BPA is equal to angle BAC. They're both equal to 90 degrees, right? So that's the first statement that I'm seeing, and you can write given as your reason there. The second statement that I'm seeing that is the same between the same between those triangles is the angle. This B angle is common in both triangles. So angle B is equal to angle B. Why? Because they are common. It's a common angle. It's a common angle. And since that's a common angle, that means the third angle is also going to be the same. So what does that mean? It means angle BAP in the smaller triangle, the blue triangle, this angle right up there, is therefore going to be equal to angle C. Or rather, let me write it clearly, ACB. Why? Because this is the third angle of a triangle. So if those two angles are the same, the third angle would in fact also be the same. And therefore I can conclude that triangle ABC is similar. I need to follow the logic. I'm starting at the 90 degrees, I'm going to that angle of B, and I'm ending at the C. Remember, the C also has the same dot. So this one needs to start at the P, go to the B, and end with the A. Sorry. So my reason for saying that they're similar is angle, angle, angle. And there we go. Now, I'm going to switch this and I'm going to look at the other triangle. This purple triangle. Alright, so alongside, let's do it this or maybe below. Yes, below, seems like we have space. So number one, I'm comparing the purple triangle with the big triangle. What am I seeing immediately that is the same? Angle APC is in fact the same as angle BAC. They're both equal to 90 degrees. It's given in the picture, right? The second statement, they share this angle C. So C is equal to angle C. Why? Because it's a common angle. So now with those two statements being said, therefore I can conclude that the purple angle which is there, right, is in fact the same as this angle there. So angle ABC is equal to angle PAC. And why am I saying that? Because this is the third angle in a triangle. The third angle in a triangle. And so therefore, I can conclude that triangle ABC, the bigger triangle, is similar. I need to follow the same logic of labeling. I started with the 90 degrees, so I need to start at triangle P. I then went to the B, which is that angle there. So this one needs to go to the A, and it needs to also end at C. Angle, angle, angle. And there we go. So now that I've proven that these two triangles are in fact similar to the bigger triangle, it therefore follows that therefore triangle PBA is similar to triangle PAC. And why am I saying those triangles are therefore similar? They're similar because they're in fact similar to the bigger triangles, because they're both similar to triangle ABC. So if they're both similar to the bigger triangle, they in fact both need to be similar to each other. And so this concludes that therefore triangle ABC is similar to triangle PBA is similar to triangle PAC. And there we go. We've proven that. And so that's how you'd go about proving this theorem number 3. I hope this makes sense. You can pause the video, make sure you're copying down the notes. Let's move on to theorem number 4, the last one. All right, down to the last theorem. If you've made it this far, then yeah, you nearly there. You're 90% there. So this is the Pythagoras theorem, and this is the theorem, the proof of the Pythagoras theorem. We are asked to prove that AC, which is the hypotenuse, is equal to AB squared plus BC squared. So what do? We need to construct something. And the construction I'm going to do is this line here, which is the AP line. And I'm going to construct it in such a way that it's perpendicular. So I'm going to construct the BP line so that it's perpendicular to the AC line. I hope that makes sense. I mean, you can see it in the picture. Then I'm going to state that since I know theorem number 3, I know that this triangle up here, me knowing theorem number 3, I know that this triangle up here is in fact similar to the bigger triangle, which is the ABC triangle. So me knowing that, therefore, it tells me that the sides are going to be proportional. But let me state that first statement, is that triangle ABC is similar to triangle, let me label it correctly, this will be APB. And so since they're similar, my reason for saying that they're similar, this is line from vertex, from the right vertex, perpendicular to the hypotenuse. So this is the reason for the previous theorem, right? And so that I've stated this, I can therefore conclude that therefore the sides AB divided by AP is equal to the sides AC divided by AB. Why? Because this is what happens when you have similar triangles. The sides are proportional. So now that I've stated that, I can cross cancel or cross multiply just to get AB by itself. And this tells me that AB is going to times this side and the AP is going to times that side. So AB squared is equal to AC times AP. Those are the first couple of statements I've stated. Then the next statement is that I'm going to now assert that this smaller triangle down here is also similar to the bigger triangle. So let's state that triangle ABC is similar to triangle, I just want to label it correctly, BPC. And why? This is again the line from the right vertex that is perpendicular to the hypotenuse. Again, this is the reason for the previous theorem, right? So now that I've stated that, I can also make some sides proportional to each other there. I'm going to make particularly the BC side there. So I'm going to have BC divided by PC is equal to the AC divided by the BC. Where am I getting these sides? I mean, you can look there. I'm saying that this distance here divided by the distance there for the smaller triangle is going to be the same as the distance of AC divided by the distance of BC, this distance there, right? I hope you're seeing it for each of those triangles, right? So yeah, I've stated those two things, and now I can cross cancel. So BC squared is equal to AC times PC. Why? Why did I state this guy at the top? It's because of similar triangles. And now that I've cross-cancelled that guy, I can actually add these two guys. Those are the two sides of the triangle. Just trying to see, what do I get when I add those two sides? So AB squared plus BC squared is in fact just AC times AP plus AC times PC. And if you take out the AC side as a common factor, you get an AP plus PC. And if you look at the picture closely, you will see that AP is in fact this distance here, and PC is in fact this distance there, and added together they give you this total distance, which is the AC distance. So this guy here in the brackets actually simplifies to just be an AC. So AC is being multiplied by AC, and so AC squared is equal to each one of these. Just going to write them down here. AB squared plus BC squared. And there we go. This is Pythagoras. I hope that makes sense. So yeah, this video concludes all the proofs that you need to know for Matric. It obviously does not include the ones that you've learned in grade 11. You do need to check out my other video on those. But on that note, bye.